The next approach I want to discuss is the contrastive learning, which is very popular and is able to outperform, the aforementioned pretest task. So the idea is very simple. Okay, so if you look at this GIF or animation here, right? So the input will be the original image, right? So here is a dog. This is a chair, right? You generate two copies of the data, right, through data augmentation. Okay, here maybe doing the color to grayscale, and this another augmentation is doing the crop and the resize and maybe change the color a little bit. Okay, so these are basically two different augmentations conducted on the original image, right? You generate these two augmented version, okay, and you go through this CNN network you are trying to train. Right, and the goal is that because these two augmentations come from the same image, right, from this original dog image, in the feature embedding space, they should be close to each other, right, because they corresponding to the same image. Okay, but if you take another image, right, you do the same, right, generate two augmented version. And if you take one of the representation from the dog and another representation from the chair, the goal is that you want the feature embedding space, their distance should be large, right? Because they corresponding to two different image, right? So that's you will see later here. There's a repel, right? So these two different images and their augmented version are considered negative pairs, right? But these two augmented version coming from the same image, they consider the positive pair, right? So we want to attract each other, right? So the distance should be close in the feature embedding space. So that's basically the idea of doing this kind of contrast learning process. Okay. Formally, what you can do for contrast learning is that you can randomly sample a mini batch of n inputs x. And you can apply two different augmentations, right? Operation T and T prime, right? So you're resulting, two, each image will result like two augmented sample, right? Xi tilde and Xj tilde, okay? And then you can apply, a base encoder, right? So the CNN network or maybe other network to extract the features, right? So we have a HI and the HJ here. And then you can apply, a fully connect layer like a projection head to form a low dimensional feature embedding. And because this two copy, right, Xi and Xj come from the same image, it's just two different augmentations. In the embedding space, we want them to be close to each other, right? So we want to maximize the agreement. On the other hand, if we have a different image, right, Y here, or maybe X2 here, you generate this two augmented version, and in the feature space, you want these two embedding to be far away because they come from two different image. Okay. So mathematically, right? So for a positive pair, we calculate the cosine similarity, right? So this is one measure of the similarity. Of course, you can using other similarity like L2 distance, but commonly we can using the cosine similarity to measure the similarity between these two vectors. And so the contrastive prediction task, right? So the positive pair should be close to each other, and the negative pair should be far away from each other, right? So if you look at this, call this NTX normalized temperature scaled cross entropy loss here, right? So we want to minimize this negative log loss here. Basically, you want to maximize this log loss, right? So I don't know if you guys still remember the log loss here, right? So you have look like this, right? You have a 0 and here is 1, right? So if you want to maximize this log loss, which basically this term has to be close to 1, right? So you want to essentially you want to maximize this here, the similarity between the positive pair, right? So this is what we want, right? We want the positive pair to be as close as to each other. So the cosine similarity can be, close to 1, okay? So through this, we can, through this learning objective, we can train the network so that the network is able to learn a very good representation from the unlabeled examples. And then we can use the learned representation, right, which is this F, okay? So this corresponding to the network, maybe a CNN or maybe other network. We're using this as the feature extractor, right? And we can fine tune it on the downstream task. Okay, so that's contrastive learning. So any questions for contrastive learning here? So which is basically the SimCLR paper proposed.
One thing on this slide, in the denominator of the cosine similarity, it should be Zi and Zj, right?
No, this is the negative.
Or above that.
Zi
like
and
the denominator of the equation above.
This one?
Yes.
Oh yeah, you're right.
Okay.
Sorry. Yeah, this is Zi and Zj. Yeah, you compare this the cosine similarity. Yeah. Thank you for pointing that out. Yeah. Okay. So because we generate the positive pair through data augmentation, right? So the data augmentation actually plays an important role in terms of the final performance of the self-supervised learning. So the author experiment with different augmentations, right? Here they have crop resize, flip, color distortion, rotation, Gaussian noise, Sobel filtering. So they experiment with different data augmentations, and they have some conclusions, right? Which one perform decent, or some of the augmentations maybe perform similarly. So this still is an open research question, right? So there's a follow-up research trying to design or automatically design, right? What is the optimal augmentation it can be performed for this contrast learning task. So if you're interested in the details about the data augmentation technique, you can refer into their original paper, okay? So they also do some evaluation, right? So first is they do this linear evaluation. So basically, SimCLR is their self-supervised learning method, right? You do the self-supervised learning, right? Remember, once it's trained, we keep the H, right? The feature extractor. I think F, okay, F here. Then you do this linear evaluation. Basically, you freeze that feature extractor, right? And you train maybe a linear classifier, right? Just one layer to do the linear classification. And basically trying to evaluate, right? How good is this feature extracted or learned by this network, right? Similarly, we do this for the supervised learning, right? So we use the feature learned by the supervised learning task, and we also do this linear evaluation and trying to, they do this for different data set, right? This all classification tasks. So food is classified different foods, right? CFAR 10, CFAR 100. Okay, so based on the result, right, the SimCLR representation even outperforms the supervised trained network, right, on this particular data set, food data set. This kind of indicating the learned representation is more generalizable as the supervised trained network. As we mentioned, right, the self-supervised learning, the number of training data is not limited, right? Essentially, we can collect a large amount of unlabeled data and do this self-supervised learning, right? So the representation may be more generalizable as the supervised representation based on a specific training set, okay? And here another example, right? So this Song 397, right? So this self-supervised learning still is again able to outperform the supervised training task. So they do this kind of like 10 different image data set trying to get a holistic view, right? How good is the representation through this self-supervised learning, okay? So that's the linear evaluation. They also do the fine-tuned result. So basically, once you train the self-supervised learning, right, you can, when you do this downstream data set, you can fine tune this entire network to do the classification. And again, they compare with the supervised, right? This is supervised on ImageNet and fine tuned on the food or Cephar 10, right? Again, some of the data set, the self-supervised pre-trained and fine-tuned is able to outperform fully supervised pre-train and fine-tune. Okay, so that's the evaluation they conducted to do to evaluate the transfer learning performance. The next approach, which is the recent one called masked autoencoder. So this network, this self-supervised learning approach is designed for vision transformer, right? So we've talked about vision transformer architecture, right? So the basic process is you divide the input into small patches, right? And then what the masked autoencoder doing is you mask out some of the patches, right? In this case, you mask out these patches and only a couple of them are visible, okay? In their approach, they mask out like 70% of the patches. So only 25% of the patches are remained, okay? So they feed these left or visible patch into the encoder to generate a feature. And also on the decoder side, they reconstruct the mask out patches, right? Basically, you reconstruct entire image. So this is, again, you can think of this is like an impeding task, right? You mask out some of the patches and you do this kind of reconstruction task and you reconstruct the missing patches. And once this network is trained, right, you can using this encoder architecture as like a pre-trained model for the downstream task. So you can remove the decoder. Basically, you're just using the encoder as the pre-trained model for the downstream task. You can using that to fine-tune on downstream data set for image classification, segmentation, or detection. Okay. Here are some examples for mask how much patches have been masked out, right? And the center is the reconstructed image, and this is the ground truth, right? So based on these examples, right? So this autoencoder approach is able to reconstruct the missing pieces, to a decent job, right? To some of the textures, the colors is still able to be preserved. And this is their comparison. And compared to other pre-trained approach, right? So this MoCo is another contrastive learning approach, Dino as well. So this is their performance. They all using this VIT architecture as the backbone to do the feature extraction or feature representation learning. And the masked autoencoder is able to outperform these other approach. So if you are interested in more on self-supervised learning approach, so I list a couple of the recent or popular self-supervised learning approach. So you can take a look. It's for example, this MoCo and the BYOL, right? And some of the recent ones, SimCLR, which don't have this negative sample pair. So they only using the positive pair to do this kind of contrast learning, okay?